Hello, my name is John Fowler. I'm the Motorola Professor of International Management in the Supply Chain Management Department of the W.P. Carey School of Business here at Arizona State University. So I'd like to talk to you today a little bit about some of the opportunities for ITSI countries. And I'm going to give you some background on the industry in order to set the context for that. So let's start with this picture that tries to show the major elements of the semiconductor industry. All right. And this is inspired by work by the Semiconductor Industry Association reports they've done where they talk about four major parts of the semiconductor supply chain. So we'll get to that in just a moment. But the first thing they identify is over on this far left side is pre-competitive research. That's where companies that compete with each other, semiconductor companies that compete with each other, get together and work on things that are 20 or so years out in terms of that. So the classic example of this these days would be the extreme ultraviolet photolithography equipment was actually started probably 25 to 30 years ago by this pre-competitive research where Intel and almost all the major semiconductor companies got together and said, we're going to need this at some point to make our really advanced computer chips. So they got together to work on that. Ultimately, it ended up becoming a product by ASML in the Netherlands. So that's pre-competitive research. It's followed by design, and I'll talk more about that in a moment. There's a piece where you do the wafer fabrication piece that makes up these basic 6 steps that get repeated over and over again. In order to do that, you have to have a lot of materials. You have to have the right equipment to do that. Then it goes to the assembly, test, and packaging area, or ATP area, to be put into, you take the wafer, cut it in the individual die, put it in a package so it can be sold. And then it goes either directly to an end customer. That customer might be a Dell Corporation, for instance, or it might go to a distributor who sells it to many different end customers. Okay, so I'll go through each of those pieces in a little bit more detail. So again, I mentioned pre-competitive research. I've already talked mostly what I wanted to say about that. Next is design. Design is very, very complicated these days and requires lots of highly trained engineers, electrical engineers mainly, in order to design the next chip. In the old days, they could make that, and it would be, maybe 2 or 3 people and take, not very long to do it. But now for advanced chips, it takes, multiple years of effort of a large team to do it, and they couldn't do it without this automation software. So this is one of the key drivers of the industry, is this automation software that helps them design these really, really complicated integrated circuits that we have today. Okay, so moving on. This is the part where we end up, again, going through wafer fabrication, where it goes through this series of 6 steps. I won't go into all the details of all this, but we'll say that it requires very, very precise materials, okay, and also requires equipment that is really, really quite powerful. In fact, the equipment is really much of the intellectual property of the industry these days is actually in the equipment. All right, so I contend that ASML is probably the most powerful player in the industry, at least in terms of new advanced chips, because they're the ones that make the only equipment that's able to produce things at the very smallest line widths needed for advanced chips. Okay, so that's, again, the wafer fabrication process. Once the wafer has been made, it's sent on to the assembly, test, and packaging area, where it's cut up into the individual chips, as I said, and put into a package, and then ultimately, again, sent to the customers. So this is just a little bit more blown out version of that, showing that the semiconductor supply chain is really far more complicated than what I showed. That was just a very high level view. This one gets into a little bit more detail, and it's in our ASU colors, maroon and gold here, put together by one of my colleagues, Dale Rogers, who many of you will meet if you go through the supply chain training that we're going to do. And so this, for instance, breaks down assembly, packaging, and test and say, not only do you need the wafers coming in, all right, you need the proper epoxy. You need the right wire bonding equipment. You need lead frames. So all those things that go into making up that. And so this is what we think about when we think about the overall supply chain. And it's for an individual company, it's really, quite complex. So semiconductor chips, what are they? They're really these highly miniaturized integrated circuits, and they have thousands of components. So this shows a wafer that has a bunch of the chips already made on it, and they're ready to be cut up and put into the individual components. So the raw wafers are these thin discs made of silicon or gallium arsenide. They're various sizes. The largest these days are about the size of a medium pizza. And so anyway, there can be up to 1,000, maybe even more than that. Chips can be produced on each wafer, and that depends on the product. Some products have a larger footprint, and so therefore you can't put as many on an individual wafer. So diving into that a little bit further, the electronic circuits are built up layer by layer in this wafer fabrication facility, or what we just call a wafer fab. The wafers are then sent to an area called probe, where the electrical tests identify which ones are good and which ones are not good. A little historical reference here. You notice that we show here that you've gone from a raw silicon wafer to one where we put the patterns on it. In this case, we've got these black dots. The black dots represent the fact that historically what's happened is you would have the wafer and an ink dot would be put on the, once they got probed, they would put an ink dot on the ones that were not good to make sure that those didn't get picked up and put into a package. No reason to spend any more money on those. Those just became scrap, essentially. So these days, you don't need to put the ink dot on it. A, it's messy, and B, we have an electronic map that can handle that. Okay, this whole thing is called the front end. So when you hear front end, that's what we're talking about. We're talking about wafer fab and probe, okay? These are typically done in one of about 6 countries, all right? The US, China, Taiwan, South Korea, Japan, or in Europe, maybe Singapore, so maybe it's 7 actually, okay? But in that is mostly an electrical and chemical process that happens there. Clearly there's some mechanical processes that take place as well, moving the wafers around, et cetera, but for the most part it's a chemical process, I would say. Okay, next the wafers are then cut into the individual die. That's called what we call assembly, okay? And then put into a package, all right? And then they're sent to test. So we call this the back end. So if you hear the things referred to as the back end, that's what we're talking about, is this assembly and test. This has been done in other places, not the 6 or 7 that I mentioned before, and it's due to high labor cost. I'll talk about that more in a moment. So this chart is just so when you get the slides, you can see I've now identified the front end is this part and the back end is this part over here. All right, so this is a slide that I borrowed from our friends at SIA, the Semiconductor Industry Association. That really shows the semiconductor industry is very global, all right? And so even an individual chip that goes into some product that you made has probably been around the world and maybe more than once. All right, so this is going through a little bit of a typical flow. So you might have a chip design here in North America, okay? But the silicon ingot, that's a raw wafer that's built up, has been done in Asia, okay? Then it comes over, maybe this is to Chandler, Arizona, to Intel or some other company in the US. Could be other places, but in this example, this would be in the US. They're done there. Then their finished wafers are sorted and maybe cut into die, though that may take, the cutting it often takes place over in Asia, which is the next step over here, number 5, where the die are assembled, tested, and packaged, okay? And then they're finally shipped for inventory, all right? And then they'll go into consumer goods, maybe. Maybe that's, again, for Intel, that would be a microprocessor that might go into a Dell computer, which would then get sent back to the U.S. possibly, okay? Obviously, there's lots of customers in the other parts of the world as well, but this is one example. I've seen estimates of 25,000 miles for an individual semiconductor device, that it might have traveled that long. I've seen estimates of maybe it crosses 70 borders at times. So one of the things that keeps the industry going well is the fact that there's fairly low tariffs. There's a big agreement that on semiconductor devices. Okay, so let's take a little bit of look at the history of the industry, because I think it's important for you to understand the overall context, okay? So integrated circuits first developed in the 1950s, late 1950s. One of the co-inventors of it, Jack Kilby, who worked at Texas Instruments. I actually have a 6-inch wafer on my desk that's signed by him. My daughter works at Texas Instruments and was able to get me this wafer. I have it until I pass away, and then she gets it back. All right. But anyway, so that was in the late 50s. United States was the industry leader. The industry really built up in the United States. And the early semiconductor companies did all the design work, the wafer fabrication, the assembly and test. In fact, they actually built a lot of the equipment that they needed to actually do the processes. This was as the industry was getting started up. Fairly early on, though, they decided that they would do the assembly and test pieces in places with cheaper labor. All right. So at that point, they went to Mexico, Central America, and also into Asia, where they could get cheaper labor. So, but companies that do all of the steps in-house by themselves are called integrated device manufacturers, okay, so, or IDMs. Okay, so a little bit more on the history. In the late 1980s, for instance, in the 80s, the Japanese government decided to invest pretty heavily into the industry, but their focus was on memory chips, all right? So DRAMs are a type of memory, dynamic random access memory. They actually flooded the market, and there were antitrust violations, et cetera. There was all kinds of lawsuits that went about, but they started taking over a large portion of the industry. And some of you may have heard of Semitech, which was a U.S. R&D consortium of semiconductor manufacturers that got together along with the Department of Defense to try to stop that, and they formed something called Semitech at the time. If you want any more on that, send me an email and I'll be happy to provide you a little bit more information there. I actually worked at Semitech for 5 years. So it turns out around this same time, Singapore, South Korea, and Taiwan also began investing in the industry. Europe was also involved in the industry to a little lesser degree. Korea also focused on doing the DRAMs, all right? So they said, we're going to go in about memory. And today, there's only about 3 companies still making memory at any kind of scale, and 2 of them are Korean companies. The other one is U.S. company Micron. Okay, but Taiwan took a little different approach, all right? They said, we're not going to try to get into the industry via DRAMs. They focused on providing contract manufacturers, that is, wafer fabrication services, for others, okay? So they weren't going to design a product, okay? They were going to manufacture the product. And there was a big market for this because the cost to build a fab, a wafer fab, became very, very expensive, all right? Remember back in the early 90s, there was talk of it being $2 billion, which today doesn't sound like very much, but at the time was a lot of money. And a lot of companies that wanted a product made didn't have enough, they couldn't afford to do that for the limited amount of products that they needed to make. So the Taiwanese companies jumped in and said, we can do that. We can make it for you. It won't be our product. It's your product. You do the design, give it to us, and then we'll make the product for you. And so those companies included TSMC, which is now the largest semiconductor manufacturer in the world. And this is called the foundry model. So when you hear the word foundry, that's talking about a wafer fabrication facility that makes products for others. Okay? So, and the foundries account for about 35% of the overall wafer fab capacity in the world. And fabless companies are companies that design their chips but then have them built in a foundry. So we also have to talk about what happens on assembly and test. Well, there's something called outsourced assembly and test companies, OSATs, and those are contract manufacturers but for the back-end operations. So a company that's a fabless company, for instance, Apple is a fabless company. They design their own chips. They have them made by TSMC, and then they have to be put into a package and tested by another company, and that would be by an OSAT. And China and Taiwan account for almost 60% of all of the back-end operations. That's a heavy concentration in an area where there's a little bit of tension between China and Taiwan, right? And so there's a real concern that what happens if those tensions escalate and there's a blockade or there's actually an invasion, et cetera. And that's really been the purpose of the ITSI program, is to be able to help countries that are friendly to the U.S. Come into play and be able to help pick up that slack in case there's something that happens there. There's also the problem that, more fab capacity is going to come online because there's more and more need for computer chips, for automated vehicles, for all this AI work that's really big now. So there's a lot of need for that, and I'll touch more on that in a moment. But back to the thinking about the different types of companies, we have the integrated model, all right, which is the integrated device manufacturers who do all their design work. They also do their front-end work, and they do their back-end work, okay? We also have the foundry model with layer specification, or the fabless foundry model, if you will, where you have a company that does a fabless design. They pass it to a foundry in order to produce the wafer that's got the chips on it, and then they send it to an OSAT to be cut into a package and tested, all right, and then back to a customer. Now, I show that as these being, you're either in this or this, okay? But an integrated device manufacturer, such as an Intel, might actually have some of their work done in a foundry. Maybe it's a product that they no longer want to make. It's an older generation product. Or maybe it's just some new product that they need for some purpose, but they don't want to use their own capacity for it. So they might use a foundry. They might also use an OSAT, all right, to do the assembly and test on that work. Okay, it's interesting times. Intel has announced that in addition to being an integrated device manufacturer, they're going to have foundry services. So in that sense, maybe this is like an IDM 2.0. I've heard that reference some. Okay, so the lines here are getting a little bit blurry, but it's important to understand the difference between an IDM company coming and one that's an OSAT. Okay, so for those ITSI countries, again, you might be able to attract an integrated device manufacturer to put their facility to package their products, package and test their products, or you might be able to attract an OSAT to come with make products, do the assembly and test for lots of different companies. Okay, so this chart, and I'll leave it for you to look at later, just identifies all those different pieces that I talked about and where they are in this overall supply chain. All right, so this shows the different types of semiconductor companies. It's not completely exhaustive, but it covers the bulk. So we've got the integrated device manufacturers, fabless companies, the foundries, the OSATs. This is also would be part of the integrated device manufacturer is assembly and test, but they've got the semiconductor equipment that goes in. Got to have this complex equipment to make semiconductor devices. You have the electronic design automation software, all right, that helps support the design part. You've got material suppliers, you've got distributors, and ultimately you've got contract manufacturers who use those products. All right, so let me go through these different types and give you some examples. So integrated device manufacturers, companies like Intel, Micron, Texas Instruments, ON Semiconductor, Analog Devices, Microchip. These are some U.S. companies that again, design their products and actually make them as well. Some of the fabless companies that you might recognize, we have Apple, NVIDIA, Qualcomm, AMD, who at one time was an integrated device manufacturer, but split their company into two companies, one being AMD, which now does the design of chips, and Global Foundries, who did the manufacturing. Now Global Foundries does work for lots of different companies, and AMD has some of their work done by other foundries. Okay, but originally the two were one company, Marvell and Altera. Okay, I probably should have had NVIDIA on top of Apple these days, just because of the work they're doing in AI and how much that's taking off. In terms of foundries, three main foundries that are in the U.S. Global Foundries, TSMC. We were thrilled in Arizona that TSMC decided to build not just one, but multiple fabs here in Arizona are in their plans. So that's really, really great for us. And then, as I indicated, Intel is also going into the foundry business. In terms of OSATs, there's really very little work done in assembly and test in the United States. In fact, less than 2% of the overall assembly and test is done inside the U.S. But one of the big companies, Amkor, is a U.S. company, but they do almost all their manufacturing in places like the Philippines, Korea, and other places as well around the world. Okay, so Amkor, and there's DECA, a local company here. Notice that this says assembly OSAT, the OSAT, but again, the U.S. IDMs also need assembly and test work done. And then in terms of the equipment, here's some of the equipment. The big U.S. companies, Applied Materials, Lam, KLA, Teradyne on the test side, Plasitherm, and then Kulicke and Safa is big in the equipment for the back end work. Okay. Finally, this is the electronic device automation software, and the six main companies that make up the bulk of the industry in that. And this is National Instruments here. Okay, so let's now talk about the need for assembly and test going forward. All right, so it turns out this chart, which I think is maybe 4 or 5 months old. Okay, so the numbers have actually gone up a little bit, but at that time there were 73 new or expansion wafer fabs that were being discussed. All right, or being on the plans for companies to build. 40% of those would have been actually in the U.S. So the U.S. is trying to go from about 11% of the market share in terms of doing wafer fabrication. Hopefully that's going to get up to 13, 14, 15% over the next 5 or 6 years by new capacity being brought on in the U.S. At one point, the U.S. was not too long back was in like 38%. So it's declined fairly rapidly, actually. Okay, and so 16 of those are going to be at that leading edge. Okay, so less than 10 nanometers for devices. Down here, you can see the blue indicates ones that are new construction, and the yellow are expansions. So you can see the majority of that is in the U.S. and in East Asia is where that's going on. So again, this new wafer fabrication capacity that's coming on, which is trying to meet the demand for chips, all right, means we need more assembly and test, all right? So, and all but some of the leading edge chips produced in those fabs need assembly and test. And by assembly and test, I'm talking really traditional assembly and test. It turns out that advanced packaging is more of a wafer level process, so it's much closer to wafer fabrication than it is actually to assembly and test, the traditional assembly and test. So I'm mainly talking about traditional assembly and test. Okay, Intel, TSMC, Micron, Samsung, Texas Instruments, they're all building fabs in the U.S. All right, so there'll be a lot of product made here in North America. And Intel is moving into the foundry business. That's going to increase, again, the amount of chips that are going to be made that need to be put into a package and tested. Okay, so that increased demand creates the need for assembly and test capacity in countries friendly with the U.S. Okay, also it's this increased demand and the fact that there's tension between China and Taiwan, which does 60% of the assembly and test now, means there's really a need to be able to keep the supply chains resilient so the U.S. companies don't suffer greatly if something happens between China and Taiwan. All right, that they'll be able to continue to build their products and continue to be profitable. Okay, so here's the primary opportunity out of the ITSI program is for assembly and test. Okay, it says OSAT here, but that would include for IDMs who may want to do their assembly and test. Okay, so that's the primary focus of the ITSI program. However, there are opportunities in other areas, but let's talk about for assembly and packaging and test. Okay, so what do you need to be able to be viable to do assembly, test, and packaging? Okay, you need secure sources of power. It turns out even if the power goes down for a moment, all right, for 30 seconds, let's say, all right, that some of the product will get destroyed, and that could be millions of dollars worth of product destroyed even for a 30-second outage of the power. So you really have to have secure power and probably backup generators, et cetera, to be able to handle all that. You need secure sources of water, all right? There is quite a bit of water used, so you need to make sure that you have that. Some of it will be ultra-pure water, not so much in assembly and test as in the fab, but there's still some need for that. You need safe working conditions, okay? No company is going to be willing to put in a facility in a place where no international company, at least, is going to be willing to put into a place where there are not safe working conditions. If there's child labor, et cetera, that's, not be acceptable. You need a stable government. You need to, if you're going to make a huge investment, you want to make sure that the conditions aren't going to change so radically that you can't be competitive. You also need a supportive government. It turns out that if you took a chip made today, all right, in the U.S. and one made in other parts of the world, that the chips made in the U.S. have about a 10% subsidy. So it's not like the government has done nothing, but there's been about a 10% subsidy on the cost of that product. It's about 30% in the rest of the world. So that's not an even playing field, all right? That was, again, a big purpose of the CHIPS Act, Chips and Science Act, was to try to address that and to try to have the government more supportive of the industry. And we had something rare happen in the United States on that, and that is we had bipartisan support for that. That doesn't happen very often these days. Okay, you also need the talent with the appropriate skills, and that's a big part of what we want to do in the ITSI program is make sure that the talent is also available. And this one is a little bit self-serving, but don't forget that not only do you need electrical engineers, chemical engineers, again, not so much chemical on the assembly and test side, a lot of mechanical engineers and robotic engineers for assembly and test. You also need people with supply chain knowledge, all right? You still have to buy things to come into that. You need people to help run the factories, et cetera. So there are additional needs there. And we have training set aside, a week's worth of training where we come in and we talk to you about supply chain in the semiconductor industry and what's important there. So these are the other opportunities that I show for companies for the ITSI countries where they might do that. And those are in italics and in red, a little bit lighter shade of red, not bolded. Okay. So there's opportunities in design. There's opportunities for the equipment, helping make equipment, even if it's not making the final piece of equipment. Maybe it's making a subassembly for that equipment. This equipment is very, very complicated, some of it. So in the software space, there's some there. Obviously, in the materials can come from different countries. Critical minerals. There's a huge opportunity there. Much of that is in China today, and so there's a high vulnerability there. So there's a lot of opportunity there. Distributors and contract manufacturers are places to play. Notice the two that I don't show in that are still in black. One is the integrated device manufacturer, but that really is talking about the wafer fabrication piece of that, and then the foundry. So I don't think any of the ITSI countries at this point should expect to get a fab, certainly not a leading edge fab, maybe a legacy fab at some point, but it really is, I think, not realistic to think about that in the immediate term. So I'm happy to answer any questions or comments that you have on this. There's my email address, john.fowler@asu.edu. I hope this has been useful in thinking about the industry overall, how the industry is made up, and we look forward to working with you on further aspects of the ITSI program. Thank you for your time.